We consider now a more geometric example. Imagine yourself on a plane. Notice this is a function of z, x, and y, where the coefficients are all constant. So we could write this in terms of z equals a constant plus mx plus ny, which is our plane idea, or plane format. What we're wondering here is which point on the plane is going to be closest to the origin. So imagine, we'll sketch it out here. Maybe it's not the plane that we're talking about here, but let's say it looks like this, but it goes up maybe further there. We can imagine there's some point on the plane that's going to be closest, have the closest approach towards the origin. So geometrically, the question's fairly intuitive. The challenge is to turn it into algebra so that we can actually solve for the coordinates. What are the x, y, z coordinates of this point? All right. Well, we know something about the relationship between z, x, and y we can pick. Otherwise, we just pick the origin. The origin is closest to the origin. But no, we have to be limited to this plane. So what can we do with that? Well, we need to take our point, distance between x, y, and z, to the origin. Well, we know that that's going to equal the square root of x minus 0 plus y minus 0, the distance in x, distance in y, and distance in z, and we're going to square it and square root it. Now, we know that once we have our function, we're going to differentiate it. I'm looking at that square root thinking, oh God, I do not want to carry around that square root for the entire time that we're doing our calculus, because we'll have a nasty chain rule thing. It'll be a real mess. So I just make a note here. This is a very commonly used approach or trick. Minimizing the distance is the same thing as minimizing the square of the distance, and the square of the distance is a much simpler formula. The square of the distance is much simpler. Or let's say it the same way, it's a much simpler formula. So we could optimize this function, but imagine differentiating it. You'd have 1/2 coming out front and divided by, then this all to the negative 1/2 power. It'd be a real mess. The distance squared is simply equal to x squared plus y squared plus z squared. That's going to be much easier to differentiate. And here's the important reason we can do this. If I have a small number and I square it, it's still smaller than any larger number when I square it. So there's an equivalence here that the smallest distance is going to correspond to the smallest distance squared point. All right. Let's start this on the next page then. We're going to need our function, or our surface here, our plane, 5z 2x plus y. So we have 5z plus 2x plus y equals 2. That's a constraint here. And I would be tempted here just to solve for y. Whatever the y value we pick is, it has to match, or it has to satisfy 2 minus 5z minus 2x. And that means our distance squared can be written as a function of simply x and z. It's going to be x squared plus y squared. Let's put that in here. 2 minus 5z minus 2x. All of that is our y value. We square that, and z squared. So now we've reduced our problem to simply optimizing this function, and we're guaranteed that our point that we pick when we pick x and z, the y value will work out so that we're on the plane that we need to be on. So again, we've seen this kind of motif of using one of the earlier values or earlier equations to constrain or isolate one variable. So we eliminate y from the distance squared. Okay, once we've got our formula here, this is our goal now, is to minimize this function. minimize the distance squared, and so that means finding critical points. So what do we get here? Let's call this f of xz, and then we can start doing our differentiation. The x derivative, 2x. Derivative of this will be 2 times the entire expression again, times the derivative of the inside, and careful, it should be negative. Let's not lose signs this early in the problem. Times negative 2, and the derivative of z with respect to x is 0. The z derivative, 0, 2 minus 5z minus 2x to the power 1, times negative 5, the derivative with respect to z of the inside, plus 2z's. All right, and of course we set them equal to 0 for critical points. Equals 0, equals 0. And what can we have to expand? We've definitely got to expand this. We have 2x plus, minus. We have our 2 and negative 2, so we'll have negative 4, negative 8 in fact. Negative 8. 2, 5, and 2 is 20, plus 20z. 2 and 2 and 2 is 8, and it's positive plus 8x. All that equals 0. There we go. In the z derivative, what can we do? We can expand this. Notice it's minus 10 times everything. So we'll have minus 20 plus 10 times 5 is 50z. 10 times 2 is 20x plus 2z's equals 0. And we can tidy that up. We'll have minus 8 plus 20z plus 10x. There. And negative 20, 52z's plus 20x's. All right, now we're in a position to start simplifying things. Again, your choice how you want to approach this. Just looking at these two equations though, it would be so nice if we just took 2 of these and subtracted 1 of these. Why would that be nice? We end up with 10x times 2 is 20x, and then we subtract the 20x. We're actually going to get a formula just in z in one step. If you want to isolate and solve, that's fine too. I'm just a big fan of if you see a shortcut, let's take it. We multiply this by 2, we get minus 16 plus 20, that's 4. 40z minus 52z, 40 minus 12z, and we end up with 0 x's. So that tells us that 12z is equal to 4, or z is equal to 4 over 12, better known as 1/3. And presto, we have our solution, at least our value for z for a critical point. So we have z, what else can we find? We can find x. Let's go back to, let's call that equation 1, we'll call that 2. 2 subbed into 1 tells us that minus 8 plus 20 times 1/3 plus 10x equals 0. 20/3 and 24/3 will have minus 4/3 plus 10x equals 0. And so that gives us 10x equals 4/3. So x is equal to 4 over 30, or if you like, 2 over 15. That looks good. 24 plus 20, yeah, okay. So there we have our x, our z, and if we wanted to, we could find our y. We might as well. Here's our y value. 2 minus 5z minus 2x, which is equal to 2 minus 5 times that minus 5/3 minus 4 over 15. And here's where the fraction button on your Casio 911s come in handy. 2 minus 5/3 minus 4/15, better known as 1/15. Fantastic. So that defines our critical point. The x value and the z value really are the critical points for our distance squared function, and the y is the coordinate that would come along if we were limiting ourselves to the plane we were given. Last but not least, we were asked to verify that this was a local minimum of the distance function. So let's take a look at that. So critical point summary here. Critical point is x, z, 1/3, 2/15. All right. What further can we do with that? Well, we need to find our function's second derivative so that we can classify the critical point. Nope, our other variable is z, so let's go with that. Z and xz. Take a flip back to our function here. If we take the second derivative, or they take the x derivative of the x derivative, we really need this in front of us before we can calculate it, don't we? Yeah, let's grab it. So our x derivative is that. We take another derivative, we're going to get a 2 minus 4 minus 8x minus 8 plus 8, 10. The z derivative twice. We have 2 over here, but we also have 10, we have 50 here. 50 plus 2, 52. Oops, that's up here. That's the pure z derivative. Our mixed partial derivative, take the z derivative of this, it's minus 4 times minus 5 is plus 20. And that's it. Okay. So again, our d value, which would be these two things multiplied minus this thing squared, 10 times 52 minus 20 squared, that's 520 minus 400, or better known as 120. That's positive. So both concavities are the same at this critical point. And what else do we know? We know that, let's take the second derivative with respect to x, which is positive. That's concave up. So we have two directions which are concave up. And that means that a critical point that we found represents a local minimum. As we would expect, it's the closest point because it's a local minimum of the distance function. Which tells us, at the end of the day, our points were 2/15, 1/15, and 1/3 is the point on the plane that we were given. I won't write it out again, but the plane which is closest to the origin. And there we go. Hopefully you're seeing some patterns here. You'll also be seeing how long these calculations can be. You'll notice we typically don't ask for a lot in terms of the assignment problems. The lists are getting shorter, not because we want you to do less work, but because the problems simply take longer now. Also, the WebWorks self-tests, you'll notice only have 1 or 2 problems in them because, again, they get pretty long after a while. So just bear that in mind when you're planning, especially on the exam. How much time do I need to solve a question like this? Probably a while. You should budget accordingly.